Hello, and welcome to this Gresham College lecture on the music of the spheres. You just heard the opening bars of Jupiter, the Bringer of Joy. It's the fourth movement of a suite of 7 planetary portraits written by British composer Gustav Holst between 1914 and 1916. Now, Holst took the 7 planets of the solar system and translated their perceived essence into music, getting inspiration from astrology and horoscopes rather than astronomy. So we hear about the character of the planets in terms of Mars, the bringer of war, Venus, the bringer of peace, Mercury, the winged messenger, Jupiter, the bringer of joy, Saturn, the bringer of age, Uranus, the magician, and Neptune, the mystic. And this suite was so innovative at the time that it struggled at first to gain the favor of the public. Indeed, the Manchester Guardian music critic was rather flabbergasted when he first heard it in 1920 performed on stage. But by October 13, 1923, the planets had become hugely popular with critics and the public alike. On that night, Gustav Holst himself was at the baton conducting the orchestra in a performance of the planets as the opening event of the Queen's Hall Symphony concerts in London, and he was described very much as the composer of the moment, perhaps because he had managed to capture something of the modernity of the times. Indeed, a few years later, Anthony Tudor, the famous choreographer, also put some of the movements into a choreography, and we see here a picture of the Mercury scene as it was performed in Melbourne in 1947. So it was a very fresh modern music, as we heard earlier, and even to our 21st century ears, accustomed as we are to science fiction soundtracks, for example, it still feels fresh and novel. And one of the innovations that Holst introduced was, for example, the fade-out ending of Neptune, where a chorus of women was to sing from a nearby room off stage, whose door was to be silently and gently closed during the last bar until, as Holst's daughter put it, the imagination knew no difference between sound and silence. Unbeknown to Holst, exactly 1 week before the London performance he conducted, an astronomer was catching another kind of cosmic rhythm. Edwin Hubble was at work with the 100-inch Hooker telescope at Mount Wilson Observatory in California, looking for variable stars inside the Andromeda Galaxy, our nearest cosmic neighbor. Hubble was hunting variable stars because he knew that if he could see the variable rhythm, light rhythm in this case, of one of such stars, he would be able to use it to measure the distance to Andromeda and thereby settle once and for all what was called at the time the Great Debate. Was the universe small and limited to our Milky Way, or was it a much bigger entity with nebulae such as the Andromeda Galaxy, actually galaxy in their own right outside of the Milky Way? Hubble was able to measure the variable star and many others, and was indeed able to place Andromeda outside the Milky Way, thereby enlarging at a stroke the size of the universe and making it as the stage for the cosmological scene, the cosmological investigations that would follow in the next century. But we want to talk about sound in space in more than metaphorical terms today. So let's first remind ourselves about sound waves. Sound as a physical entity is made of compression waves that travel through a medium. So those waves are waves of compression and rarefaction of the medium, be it air or water or a solid. And those waves called longitudinal waves in physics, travel in the same direction, the compression is in the same direction as their direction of travel. On Earth, at sea level, sound travels at about 340 meters per second through air at 20 degrees. And so this accounts for the phenomenon that is very familiar to us of hearing the rumble of thunder a few seconds after we've seen the lightning. Light travels at a much faster 300,000 kilometers per second, and it's almost instantaneous, essentially instantaneous on Earth, while sound takes some time to propagate. But as we go up from sea level to up in the atmosphere, the air becomes thinner and thinner, and the sound progressively disappears. There is no air in space. At about 100 kilometers altitude, the air gives way to emptiness, and therefore there is no possibility for sound to be propagating in space. And every time we watch a science fiction movie and we hear one of those mighty spaceships swishing by, we know that the creators have taken some artistic license there. There is no sound in space. However, space is not entirely empty. We actually now know that there is a great deal of particles teeming through space. The most abundant of particles is photons, the particles that make up light, with 413 photons per cubic centimeter, most of them coming from the very early universe. The second most abundant particle in space is neutrinos, 112 per cubic centimeters, neutrinos that were produced just a second after the Big Bang and have been propagating ever since, becoming very, very cold and very low energetic. We can't see them directly because they are too low energy for us to be able to observe them. We also know from contemporary ideas about the makeup of the universe that there is about 5 times more dark matter than normal matter in the universe. And if that idea is true, then we expect dark matter particles, massive and neutral, to be zooming around the universe as well, about 0.004 particles of dark matter per cubic centimeter. But other than that, the universe is quite empty today, and indeed if we took all of the normal matter that exists in the universe in the form of stars and planets and people and asteroids and gas, and we spread it around uniformly through the cosmos, it would be very thinly spread out indeed. In fact, the average density would be the same as taking 2 grains of sand and putting one in London and the nearest neighbor in Sydney, 10,000 miles away. Space is very nearly empty and absolutely silent today. But it was not always thus. Space is expanding, and therefore it would be smaller. Any given patch of space would be smaller in the past. This diagram shows the expansion of the universe from left to right. Today the universe is big, almost empty. In fact, the density is very, very small, and its average temperature is very, very cold, 3 Kelvin, minus 269 degrees centigrade. In the past, however, the universe was smaller, denser, and hotter. In terms of the contents of the universe, the normal matter in the cosmos is mostly made of the 2 simplest elements: hydrogen, a single proton encircled by an electron, and helium, 2 protons and 2 neutrons in the nucleus, and 2 electrons going around it. As we go back in the history of the universe, there comes a point when the universe was so compressed and so energetic that its temperature was much higher than today, 1,000 times higher than it is now, depicted by the yellow circle in the diagram, a temperature sufficient in fact to vaporize gold, had gold existed at the moment in time. It hadn't been produced in the furnace of stars yet. The universe was also sufficiently energetic for it to glow of a nice yellow color, the same color of the flesh of a mango, let's say. If we go even further back in the history of the universe was hotter earlier on, and it would be glowing white and blue if we go to even earlier moments. But we shall stay with this moment when the universe was glowing yellow, 380,000 years after the Big Bang. At that point in time, the temperature was sufficient for the photons, the particles of light, to knock off electrons from their nice orbits around hydrogen cores. And so what happens is that the hydrogen cores, the protons, got split up from the electrons, and the universe was filled with a highly energetic plasma made of electrons, protons, and photons, the particles of light. That plasma was very, very thin, but glued together by the large number of photons that were in existence. In fact, about 1 billion photons for each proton in the universe. It was, in other words, a medium for sound to propagate through. Not exactly the same as air, but mechanically able to support the propagation of sound waves. The universe, 380,000 years after the Big Bang, was a gigantic drum ready to be played, if only we could find something to beat it with. In order to find our cosmic drummer, we need to look no further than in the world of quantum mechanical fluctuations. When the universe was tiny at the very beginning of time, quantum mechanics, our theory of how the microphysical world behaves, was important. And indeed, if we look at the scale of atoms or below, everything fluctuates all the time. The famous Heisenberg uncertainty principle. Therefore, we expect at the very early stages of the life of the universe that the energy and the density of the distribution of matter and photons would be subject to fluctuations around its average. Every time one such fluctuations gave a higher density than average, represented in this diagram by the red dot, that fluctuation would start attracting more and more matter towards it because of the influence of gravity. And so it would start growing in density and compress itself. Except photons, light, were also being dragged into the compression point as they were part of the plasma, and at a certain point the outward directed pressure from the photon would resist the compression and reverse the motion and launch off a wave that would travel through the plasma at about 60% of the speed of light. This is nothing else but the front of a sound wave. The sound wave then travels through the plasma, growing all the time as it goes along, represented by the growing size circles in the picture, until something remarkable happened 380,000 years later. The universe has been expanding all the while, it has been cooling down all the while, and at that point in time, 380,000 years after the Big Bang, it's cooled off enough so that the photons no longer have the necessary energy to keep electrons and protons apart. Electrons and protons combined to form hydrogen, and at this point the plasma disappears. The medium through which the sound had propagated is no longer there, and that means that the sound waves are frozen in their tracks. They can no longer propagate. They've covered 500,000 light years since the beginning of time, but they are stopped because of the absence of plasma. The photons at the same time were no longer impeded in their trajectories by the presence of electrons, since the electrons have been now glued into hydrogen atoms by the protons. The photons are now free to propagate in a straight line for the first time ever. The universe becomes transparent and dark. Those very photons which we see streaming from the middle of the diagram towards us have been traveling through the universe for 13.7 billion years before arriving to us and falling into our detectors, satellites, and telescopes. By looking at these photons, we can reconstruct the original temperature and therefore the original density of the regions from which they came from. And in correspondence to the crests of the waves, we expect a higher density. We also expect a higher temperature, and therefore we expect to see fluctuations in the temperature of the photons that we receive. So those fluctuations are depicted on the right-hand side in the real data obtained by the Planck satellite a few years back by different colors. So red for hot and blue for cool. And you can see this characteristic pattern of red spots and hot and blue spots, which are essentially the superposition, the intertwining of regions of space that were slightly hotter, slightly denser in red, and regions that were slightly cooler, slightly more rarefied, 380,000 years after the Big Bang. And the hot regions are in correspondence to the crests of the sound waves as they found themselves frozen at the disappearance of the plasma. In other words, we can map out with the relic radiation, with the relic light from the Big Bang, the distribution of sound crests at the end of this plasma period of 380 years after the Big Bang. By further analyzing in a statistical fashion the distribution of hot and cool spots in the map that I showed you, we can bring forth its underlying characteristic oscillatory property, which is a reflection of the sound waves that created the spots in the first instance. And we see in this diagram a clear oscillatory pattern. In red, the data measured by the Planck satellite, and in green our best theoretical guess, our best theoretical model of what the data should look like, which matches very well indeed. You see this characteristic oscillatory pattern, which is a reflection of the sound nature of the spot, of the crest of the waves that produce these spots in the relic radiation. This is a kind of a sound wave that was not made to be heard by human ears, of course. With a wavelength of 500,000 light years, if you were to play it on a piano, you would have to extend its keyboard by 65 octaves to the left. It's not something we can really hear. Nevertheless, John Kramer at the University of Washington has translated this data in a way that it's audible for the human ear, in a nice admixture of science and art. And he has produced the following track that represents the distribution of fluctuations in the light left over from the Big Bang. That's to say, the distribution of cosmic sound waves from 100,000 years after the Big Bang to about 760,000 years after the Big Bang. We're going to listen to this cosmic piece in a minute. The main thing that you are likely to notice is how it becomes deeper over time. That's because as the light emitted by at the end of the plasma epoch, as that light traverses the universe keeps expanding and the light frequency itself is stretched, and so it becomes a longer wavelength, and translated into sound, it becomes deeper. We're now going to listen in to the cosmic sound of the baby universe, what we could call the Big Bang rumble. I hope you'll agree with me, this is quite a piece of music, and in beauty it rivals anything written by Bach, in my opinion. Let's now go back to that moment when the photons were released, when the universe turns from being plasma-filled to transparent. We followed their trajectory through space until they've hit our detectors 13.7 billion years later. But we haven't really said what's happened to the matter that was being swept in a crest of a wave alongside the cosmic sound. So let's go back to that moment when the cosmic sound stops propagating because the plasma disappears. The overdensity that was at the beginning has now been expanded into a sphere 500,000 light years in radius. Along the rim of that sphere, which in the diagram is represented as a circle in 2 dimensions, we have a crest of sound, which is to say a compression point, an overdense region with more material than on average, more gas than on average. when the plasma disappears, gravity sets about its silent work of attracting even more material along the rim. The region that's dense gets ever denser because gravity attracts material onto it. It's kind of a game of the rich get richer. So we expect more and more hydrogen and helium gas to accumulate around the rim, and so that's where galaxies will eventually be formed. That's where stars ignite, and that's where we expect to find the location where we expect to find galaxies in correspondence to the crest of the wave when it was stopped in its expansion. However, we must remember the existence of dark matter. Dark matter did not participate in the cosmic sound expansion because it was not part of the plasma. It's neutral, so it wouldn't be a part of the oscillations that gave rise to the sound wave in the first place. Instead, dark matter stayed behind at the center of the perturbation, at the center or at the origin where the initial quantum fluctuation set off the sound wave in the first place. And its density grew and grew and grew all the time as the sound wave was expanding outwards. So by the time the universe becomes transparent, the dark matter density at the center of the wave is quite high, and therefore, now that the plasma is gone, it attracts matter back into the center. So we expect gas to flow from the rim, where the crest stopped, back to the center of the perturbation under the influence of dark matter. The conclusion of all of this is that the gas gets accumulated in two places, at the center of the perturbation and in a shell at the location of the crest of the sound wave when the propagation stopped, which you see depicted in the diagram as this bullseye pattern. Galaxies will form at the center and on the rim, and the same is true in many different locations in space, indeed in all of the locations where the perturbations have set off acoustic waves, sounds. So we don't expect to see bullseye patterns of galaxies in the universe such as the ones that are depicted in this artist impression. That's an exaggerated version of the story I just told you. We don't expect to see that, but in general, statistically speaking, we do expect that galaxies preferentially form in rings or in spheres in 3 dimensions around the central perturbation. The actual data about the distribution of millions of galaxies in the cosmos don't show us a bullseye pattern like this. You can see them depicted with the blue dots in the bottom right inset of the picture. Those data do not show quite so clearly this distribution of galaxies, but we can still hope to be able to tease out the preferential separation between galaxies, which was 500,000 light years when the sound wave stopped, but in the meantime has further grown because it has been expanded along by the expansion of the universe. And that distance, the distance originally covered by the sound waves of the early universe, has now grown to a mighty 440 million light years. So a very sizable fraction of the visible universe. In order to see it, we must measure the location of millions of galaxies in the sky and then use statistical tools to tease out this separation, which is still imprinted, if only subtly, in the distribution of galaxies. So in a sense, all the galaxies that we see in the sky have been surfing the cosmic sound crests, ourselves included. So we caught quite a wave, if you like, in the history of the universe. So the wave, this cosmic wave, we can catch it then. Now we can reconstruct it using statistics. And here you see the very first such reconstructions in 2005, when a team of astronomers measured the location of hundreds of thousands of galaxies and then set about looking at the probability of finding one galaxy as a function of their separation. So in our picture, looking for an excess of galaxies in the direction of the red arrow slicing through the bullseye that was formed in the early universe. And you can see that the probability of finding a galaxy away from the center, which is the distance is depicted as the horizontal axis in this diagram, drops off, but at a certain point there is a little bump. The probability picks up again. You can see it more clearly in the data depicted in the inset of the figure. There's a little tiny bump, which is not very high indeed. It's only about 1%. It's a tiny little bump that corresponds to the rim distance, the distance covered by the sound in the primordial universe. We can detect it, we have seen it, it's the little bump you see in the data, and so we can now say that in fact we have been able to reconstruct the distribution of galaxies to such a precision that we can find that the very, very thinly veiled pattern of the presence of cosmic sound waves in the distribution of galaxies in the sky. This is quite an achievement, and it's a useful one, because by measuring the way these crests behave as a function of the distance of galaxies, we can measure many useful properties of the expansion of the universe in the last 6 billion years or so, and therefore we can use it as a tool to learn about the physical nature of the universe. So far, we talked about sound and its fantastic applications in understanding the nature and properties of the universe we live in. I now want to move on and talk about a different kind of wave that is not a sound wave at all, but that shares many analogies with sound, and therefore we often talk about it in similar fashion: gravitational waves. Sound is a compression wave that travels in a medium, like we saw. There are other kind of waves that are quite different, like for example electromagnetic waves, of which light is one. Light is an oscillation of the electric and the magnetic field, oscillating in a direction that is perpendicular to the direction of motion. It travels with the speed of light, and it can travel through vacuum as well, not just through a medium. In fact, it does not need a medium to propagate, which is something that set Einstein onto the correct path to special relativity when he considered the issue in 1905. Now, electromagnetic waves we're very familiar with because they are in almost every piece of technology we nowadays use. And in fact, it's very, very simple to manipulate them, and we've been doing it for a couple of hundred years now. And one way of simply understanding how to produce an electromagnetic wave is to think about the old-fashioned TV aerial that's depicted here, which can be used both as a receiver, as an aerial, but it can also be used as an antenna to produce an electromagnetic wave. In order to get the oscillation going, what we need is to take two charges, a positive and a negative charge, and make them oscillate back and forth in a line. This creates an electromagnetic wave, and vice versa. If an electromagnetic wave impinges on an antenna, it will set the two charges in motion, and by doing that it will produce an electric signal that can be decoded and gives us transmission through radio or radio waves, for example. So by moving in a linear pattern back and forth, positive and negative charges, we can produce or detect electromagnetic waves, and we've been doing it for centuries now. Einstein, in analogy with electromagnetism, started thinking about what would happen if you move around masses rather than charges. Now, masses are different because we don't have positive and negative masses, we only have positive masses. And the theory of gravity that Einstein developed, general relativity, is a different kind of theory from electromagnetism. Nevertheless, Einstein realized that if you take a mass and you swing it around in a way that changes its location, just like a hammer thrower does with its hammer, then this movement will produce perturbations in the fabric of space-time, ripples that will propagate out at the speed of light, and that he called gravitational waves. Now, Einstein himself was undecided whether gravitational waves were a real phenomenon or not. He proposed them in 1916, but then 20 years later he wrote a paper saying that perhaps they were not physical after all, only to be convinced to change his mind back by some colleagues. It took 100 years for our technology to catch up with Einstein's idea and to be able to measure those gravitational waves. as they are produced in space by two bodies that revolve around each other, like two black holes or two neutron stars. They propagate out at the speed of light, and eventually, when they get to us on the Earth, they change the distance between two places in space in a way that stretches them in one direction and compresses them in another. I say they change the distance. In reality, what they do, they actually change the fabric of space-time itself between the points. The points are actually not moving. It's the space between them that gets compressed or stretched in this characteristic fashion. The distortion is tiny. It's about a thousandth of the size of a proton over 4 kilometers length, which is the length of the arms of the instrument that first discovered them in September 2015, the LIGO instrument. As you can see, even commemorative stamps have been produced to sort of celebrate this great achievement of the detection of gravitational waves long after they had been predicted by Einstein. We're also able to produce sophisticated numerical simulations using Einstein's general theory of relativity of how those disturbances of space-time ought to be produced and propagate when two massive objects, such as black holes depicted here, spin around each other. As the black holes orbit around each other, they emit gravitational waves, and those waves will propagate outwards, and in doing so, they carry away energy, which means that the orbit of the two black holes tightens, which means more gravitational waves are produced at a higher frequency, more energy is purged out, the orbit tightens further and further and further until the two black holes collide and merge. And this is what we are seeing here in this simulation. If we were close enough together to see this, which is not likely to happen, this is what we would witness, presumably. Again, as a very detailed simulation of two black holes merging, deforming, and finally settling into a single entity. The dancing around of stars that you can see is an effect due to the immense distortion of the fabric of space-time that happen around such massive bodies. This is the distortion of the background field of stars that is shown as a way of mapping out how space-time is deformed by the swirling around of massive black holes. Going back to the numerical simulation of the black hole merging, you can see that the characteristic signal which is transmitted through gravitational waves goes through a phase in which the amplitude of the signal increases, the envelope becomes bigger, and the frequency shortens as the orbit tightens. Is a characteristic sound, if you like, emitted in gravitational wave that, if translated into a frequency that humans could hear, would be like a chirp, increasing in volume and in pitch as the two black holes progress in their lethal cosmic dance towards their eventual death. After the initial discovery of gravitational waves in 2015, detections of other gravitational waves signal have been quite common, actually. And so what was once a breakthrough discovery worthy of Nobel Prize for Physics in 2017 became, if not routine, common enough to enable us to study many such systems. And you see here some of them in terms of the reconstruction of the black holes or neutron stars that gave rise to the signal, and at the bottom, the shape of the gravitational wave signal that they gave off. You can see in this detail one of such systems merging and then finally settling into one final object. So here is a few of such examples of gravitational waves that have been detected by the LIGO instruments. You can see all of them share the same basic pattern. A gravitational wave signal that becomes stronger and higher pitch as the two bodies go towards the ultimate collision. In these diagrams, the horizontal axis represents time, half a second overall, and the vertical axis represents the pitch, if you like, of the gravitational wave tone that you would hear if you could pick up gravitational waves with your ears, which we cannot. However, it's a very natural thing to translate this gravitational wave signal into an actual tone and a melody, if you like, that we can listen to because of its nature as an oscillatory pattern and one that changes both in amplitude and in frequencies, just like normal sound would do. Here, I put together a couple of examples of simulated sounds that what we would hear from collisions of various objects put together by the group of Scott Hughes collaborators at MIT. So they've taken the liberty of compressing what would be a period of months or years into just a few seconds for our practicality. We wouldn't probably be able or willing to listen to simulations that last for months and years. And also they change the frequency from the original one to one that it's in the audible domain to make it understandable to us. So I got here two examples. One is the neutron star and the supermassive black hole that we're going to listen to first. So this is a big mass that is circled by a much smaller neutron star, which eventually will collide and merge into the supermassive black hole. And here it is. Towards the end, we hear quite well the acceleration in frequency, but also the increase in amplitude, which ends with a characteristic chirp at the end. Here's another example, two spinning binary black holes, similar to the kind of data that we're actually observing with the LIGO instruments today. Again, a very characteristic chirping at the end. And so by analyzing the details of this music of space-time, we can learn a great deal about the properties of the black holes that emitted those gravitational waves, about neutron stars. We can also test the theory of general relativity that predicts in detail the kind of sound and melodies that those objects ought to emit. And therefore, we have found a new tool that can effectively act as a new window, an auditory window, as opposed to a visual one onto the universe at large. Finally, a frontier of astronomy and cosmology is to use these cosmic sirens as musical signposts in the expansion of the universe. If you are lost at sea in fog, foghorns, at least once upon a time, used to blare out to give you a warning of your distance or your proximity to a dangerous shoreline. In the same way, we can think of these gravitational wave emissions from black holes as cosmic sirens propagating through the universe to us. If we can locate them, both in the sky and in distance, then we can learn how fast and how much the universe has expanded ever since they were emitted. Now, this is a really important task for cosmologists, but black holes collisions and black holes mergers do not come as standard sirens, just like foghorns have all different volumes and tones. And so by themselves are insufficient to tell the distance. However, because each one of those black holes or neutron stars mergers has got their own specific music, its own specific melody, if you like, from the tone, the pitch, the acceleration, the volume, the amplitude, from the music of the merger, we can actually learn about the characteristics of the black holes or the neutron stars that emitted them. And with that information in hand, we can use the observations to measure distances to them. And this will be one of the most important tools in going forward in the coming decade to enable us to revolutionize the way distances are measured in cosmology and thereby resolving some of the most important outstanding questions in the fundamental makeup and properties of the universe. Here's an example of a candidate black hole merger that has been localized on the sky purely by auditory means, purely in virtue of its gravitational wave signal, The red dot at the middle is not light. It's the location, is the reconstructed location of the black hole merger using only gravitational wave signals. So astronomy is becoming an auditory science, and that's wonderful for many reasons. First, because it will enhance our capability to map out the universe, but also because signals such as gravitational waves are naturally translated into sound, which is something that is more accessible, more inclusive, and can be, for example, used to communicate astronomy and even the content of the data to people, for example, with visual impairment, people who have never been able to see the visual side of the universe. 2.5 millennia ago, the Pythagoreans believed that each one of the 7 planets, among which they counted the Sun and the Moon, produced a sound as it revolved around the Earth, a kind of note that would fill space with the most perfect of harmonies, which they called the diapason, the concordance of all the notes. They could not have imagined that in the 21st century, real sound and other kind of waves coming from the depth of the cosmos would reveal to us an equally beautiful, even more intricate cosmic symphony.